Good morning students. As we saw in our previous video on the difference between microprocessor and microcontrollers, a microprocessor is an IC which only has a CPU inside it. It does not have RAM, ROM or any other peripherals on the chip. A user system designer has to externally install these peripherals to make the system functional. In contrast, a microcontroller is a device that consists of a fixed RAM, ROM and other peripheral like timer, interrupt, ports embedded on a single chip. Since the application are specific, it requires a small amount of on-chip RAM and ROM, which in turn reduces the cost, size and removes overhead in terms of having to interface everything before having a workable computing device. In this video, we will learn about the internal RAM and ROM of 8051. We will also discuss the addition of external memory. However, the actual interfacing part is covered in a separate video. Let us take a look at the flowchart depicting the general classification of memory in an embedded system. Read-only memory ROM is a type of storage that permanently stores data on electronic devices. It contains the code or program that is needed to start. It performs major input-output tasks and holds program or software instructions. Random access memory RAM is the main memory in a computer and it is much faster to read from and write to than other kind of storages such as hard disk drive HDD, solid state drive SDD or optical drive. The basic difference between a microprocessor and microcontroller is the on-chip memory. A microcontroller consists of an on-chip RAM, that is data memory, and ROM, a program memory. The program memory is used for permanent saving of code or program that is to be executed in the program counter. Whereas data memory is used to temporarily store intermediate results and variables. For a CPU to process the information, it should be stored in either RAM or ROM. These are referred to as primary memory. The program memory or ROM is a type of non-volatile memory used in microcontroller where the code or the program to be executed is stored using the program counter, like tables or initialization program. Intel 8051 has an internal built-in ROM of 4 kilobytes and can be extended up to 64 kilobytes by using an external program memory. The program memory allocation can be done in two ways depending on the status of the external access pin EA, which is an active low pin, that is activates when low signal is provided. In case of 4 kilobytes of internal ROM, the address space is from 000H to 0FFFH. If the address space, that is the program address, exceeds this value, then the CPU will automatically fetch the code from the external program memory. For this, the external access pin EA pin must be pulled high. That is, when EA pin is high, the CPU first fetches the instruction from the internal program memory in the address range of 0000H to 0FFFH, and if the memory address exceeds the limit, then the instruction are fetched from the external ROM in the address range from 1000H to FFFFH. There is another way to fetch the instruction, that is ignore the internal ROM and fetch all the instruction only from the external program memory. For this scenario, the EA pin must be connected to ground. In this case, the memory address of external ROM will be from 0000H to FFFFH. The data memory or RAM is a volatile memory. Since cutting off power to the IC will result in loss of information or data. RAM is used for temporarily storing the data and the auxiliary result generated during the runtime. The data memory in 8051 is divided into three parts: lower 128 bytes, upper 128 bytes, and additional 128 bytes of memory. The lower 128 byte, that is from 00H to 7FH, which are addressed either directly or indirectly. Further, the lower 128 bytes are divided into three parts as register banks, that is bank 0, bank 1, bank 2 and bank 3, starting from 00H to 1FH of 32 bytes, and bit addressable area from 20H to 2FH of 16 bytes, and general purpose register, that is scratch pad area, from 30H to 7FH, that is of 80 bytes. The upper 128 bytes starting from 80H to 0FFH is for special function registers, which includes IO ports, port 0, port 1, port 2, port 3, accumulator, timer, interrupts, serial communication controls, program status words. These are addressed using direct addressing. You know registers as something that is used to store information temporarily. But dividing into register banks is an interesting concept that helps utilize memory effectively. It allows you to address an entire range of memory using just the register's name. The 8051 has 4 register banks, with each bank having 8 registers, which are used in many of its instructions. These registers are numbered from 0 through 7, that is R0, R1, R2, R3, R4, R5, R6 and R7. These registers are generally used to assist in manipulating values and moving data from one memory location to another location. For example, to add the number 0A, 0B and 0C, we would execute the following instruction. By default, bank 0 is selected. Move R0, 0CH, that is immediately load the 0C to register R0, and this instruction state immediately load 0B to R1, and this instruction state immediately move the data 0A to accumulator, and add A, R1 will add the accumulator content with respect to R1 register content, and it is again saved in the accumulator, temporarily saved in the accumulator. Then add A, R0, what it is going to do is it is going to add the content of register R0 with respect to A. This R0, R1, R2 to R7 registers are much similar to that of the general purpose registers what we have seen in our 8085 microprocessor. These register banks are accessed one at a time by bit address of D3 and D4 bits of program status word. A table is being shown here This table shows how the banks are being selected when RS1 and RS2 bits are being set in the program status word. If RS1 and RS2 are 00, then bank 0 is selected, that is memory location from 00 to 07 is being selected. If RS1 and RS2 are 01, then bank 1 is selected and the memory location is from 08 to 0F. If RS1 and RS2 are 10, then bank 2 is being selected and the memory location is from 10 to 17. If both RS1 and RS2 are 11, bank 3 is selected and its memory location is 18 to 1F. These banks are accessed one at a time by bit addressing of this D3 and D4 bits of program status word. By changing the value of RS0 and RS1, the banks are being selected. "16 bytes of RAM is allocated as bit addressable memory. It consists of 16 cross 8, that is equal to 128 bits. These 128 bits can be individually bit addressed starting from 00H to 7FH as shown in the diagram. So it is being starting from 00H and it ends to 7FH, or can be byte addressable from 20H to 2FH, 20F to 2FH. A quick analogy to comprehend this would be the one we used in our 8085. Consider a housing society with 16 lands named 20H to 2FH, which with each row consisting of 8 houses, and each house has its particular address in the range of 00H to 7FH. That is 128 houses. Now these houses can be addressed individually one at a time, or the whole land can be addressed at a time. These bits can be modified by using set B and clear command. The program status word has an F0 flag, which is a user set flag. This flag can be copied to bit addressable memory for monitoring its status. You can check out a list of all the bitwise instruction in 8051 over here. Bit addressing is very useful when we want to monitor the status of a particular pin of any port. If we want to turn on a LED on or off connecting to a particular pin, we don't need to write the content of the whole port. Instead, we can address the particular pin to which the LED is connected, by means of which we can save the memory. Let us take some example to understand the bit addressing. Clear 0FH. Clear 0FH, what it is going to do is, it is going to clear the D7 bit of RAM location 21H. That is 0FH is equal to 0. Set bit 42H. Set bit 42H. What it is going to do is, the D2 bit of RAM location 28H. This is nothing but of 28H, and this is nothing but of the bit 2 of 28H. This bit is being set to 1. Clear 67H. D7 bit of RAM location 67 is being cleared. Set bit 28H. D0 bit of 28H is being set. The rest of the RAM from 30H to 7FH, these 32 bytes can be addressed directly or indirectly using a direct or indirect addressing mode respectively. Therefore, it is also called scratchpad memory. You may read or write full bytes of data at these locations. In 8051, internal RAM can be used as stack. The stack is an area of internal RAM that is assigned to temporarily hold all the parameters of the variable, that is, its value and location. The stack is also responsible for reminding the order in which a function is called so that it can be returned correctly. The register used to access this stack is called the stack pointer. The address of the stack is contained in the stack pointer register, which itself is present at the location 80H. It is accessed by the basic move command and data is written into or extracted from the stack with the help of push and pop command. The register used to access the stack is called stack pointer register. The stack pointer in 8051 is only 8-bit wide, which means that it can take the value 00 to FFH. When 8051 is powered up, the stack register contains the value 07H. That's all about the memory organization of 8051 microcontroller. We will discuss about the special function registers in the next video.